for you. We have 6 in-person talks. I thought your reaction would be the same as mine. So I am very excited to introduce our first in-person speaker on the origins of turbulent energy spectra in a global stratified ocean model. Nicholas Kevlahan will be giving the talk.
Thank you very much. And I'll be talking today about a very idealized numerical experiment to try to understand the origins of observed turbulent spectra in the oceans. This is joint work with Francis Poulin at Waterloo, who unfortunately couldn't be here. So what are our questions? The observations show that turbulence, submesoscale surface energy spectra are something like k to the minus 5/3. And those observations come from satellites and also from a high-resolution NEMO. 2D turbulence, classic 2D turbulence, is something like k minus 3. Internal wave turbulence is maybe k minus 2. 3D turbulence can be k minus 2 to k minus 5/3 energy spectrum. What are we seeing when we look at the oceans? In a previous paper with Francis, we looked at an idealized western boundary current configuration, wind-stressed rotating flow with an idealized landmass in green, which is generates western boundary currents. And we did a very high resolution simulation on a small Earth with slow rotation, so we had a very well-resolved sub-mesoscale. This was done using a code I've been developing called WaveTrisk, which is a global atmosphere or ocean model. It normally is run in adaptive mode, so it dynamically adapts the grid, but here we ran non-adaptively. We did 1 and 2 layer shallow water simulations, and they both showed the barotropic mode had an energy spectrum of k minus 3, so not what we observe. In the 2-layer case, the baroclinic mode did show k minus 5/3 in a slow rotation case, but it was very weak. The baroclinic mode was so weak that it was not observable in the total energy spectrum. So the questions I want to ask here is what dynamics are responsible for the observed spectrum? An obvious question is maybe if we add more vertical layers, which adds more baroclinic modes, we'll gradually generate a shallower spectrum. Maybe we just need more baroclinic dynamics. How many layers are necessary? What's the role of vertical diffusion? So in real turbulence or in ocean models, you have a turbulent diffusion, a subgrid scale eddy viscosity model. What does this change? And if you plot the slope of the turbulent energy spectrum as a function of depth, what does that profile look like? How does the turbulence change qualitatively as you go from the surface to depth? And also we want to look at a dependence on Rossby number, which also changes with depth. So we use a simple eddy viscosity model for vertical diffusion. It's similar to one of the cases in NEMO. We have a 200-meter surface mixed layer that we initialize to constant density, and it relaxes to constant density on a certain time scale. Then we have a linearly stratified deep layer for a total depth of 4,000 meters. We have slow rotation and also a small Earth. So the Earth diameter is also scaled by 1/6. Why do we do that? It's so we can get really highly resolved submesoscale. We resolve the submesoscale with about 10 grid points. We put the same number of vertical layers in the surface layer and the linearly stratified layers, and we look at 4, 12, and then 60 layers, which is, I guess, the realistic case. The horizontal resolution on our small Earth is 5 kilometers, which would be 30 kilometers on the real Earth. So it's high resolution, slow rotation. We can see the turbulence. And we have hyperviscosity to maximize our inertial range. We also compare with idealized models, the 2D quasi-geostrophic model and a surface quasi-geostrophic model. And that's just our profiles of vertical diffusivity, eddy viscosity. Okay, so let's start with the 4-layer case. We've done 1-layer, 2-layer. Neither of those gave us realistic spectra. What about 4 layers? Unfortunately, 4 layers doesn't either. So what I'm showing there is the energy spectrum versus length scale. At the surface, the bottom of the mixed layer, that linearly stratified 200-meter layer, and at depth, and they're all around K-3. So this 2D type spectrum. It's not what we see. 12 layers. Now it's looking more realistic. What you want to focus on is the surface layer where the slope is around K-2. It's much shallower. That means much more turbulent. At depth, we're still seeing what we saw before in the 1- and 2-layer barotropic cases. Getting closer. 60 layers. This is now close to what you do in a real model. And we're right there. We've got something that you'll see is really converging to -5/3 at the surface, and then -3 at depth. If we put it all together, we can get a vertical profile of this power law. So what I'm showing on the horizontal axis is the exponent p and k to the power p. And you can see it ranges from about -3.8 to maybe -1.3. And on the vertical axis, it's just depth. The green line is a boundary, the top boundary of the linearly stratified region. So what you see is as you move towards the surface, the spectrum converges very nicely to K-5/3. That's its observed spectrum. And then it's got 2 other interesting regions. Where I've got my little pointer there, that corresponds to our barotropic spectrum of about K-3, K to the power -3. And then something funny happens, it becomes much less turbulent, and that corresponds to a QG model. What QG should give, I think, -3.8 or something like that. So it looks like as you go up and down in the water column, you're going from something like really strong 3D turbulence at the surface to a barotropic type turbulence at mid depths, and then a QG type turbulence. So SQG at the surface, barotropic in the middle, and QG at depth. And then we can look at the Rossby radius, and you can see the Rossby radius changes significantly with depth, and a larger Rossby number, not surprisingly, corresponds to more turbulence. And this just gives a picture at the surface, the bottom of the mixed layer, and the bottom layer of what the turbulence, what the vorticity is really looking like. And you can see even qualitatively, it looks very, very different. At the surface, you're getting a kind of almost frontogenesis type structure, which is what SQG, I guess, is supposed to model. And in the middle, it's looking like my 1-layer simulation. And at the bottom, not much is happening. So then Francis did some QG and SQG, very, very simple, idealized 2D models. So this is not Western boundary currents. It's not on this sphere. But interestingly, you see K-5/3 for the SQG, which is what we see at the surface. And in fact, we compare it with -4, but it's really about -3.8, which we see as well. So it seems we're seeing the signature of all 3 types of models here: SQG at the surface, a barotropic shallow water, one sort of model at mid depths, and even some quasi-geostrophic at depth. So the conclusions: I performed 412 and 60-layer stratified Western boundary current sub-mesoscale simulations with vertical diffusion defined using an analytic eddy viscosity, and that's diffusion of buoyancy as well as momentum. Don't forget, I had previously done 1 and 2 layer cases, so we really have a complete picture. The 4-layer case basically behaved as in the 1 and 2 layer cases for the barotropic mode. And the 12 and 60 layer cases were showing results very similar to what we observe in simulations and observations of ocean turbulence. Turbulent spectra are associated with larger Rossby numbers in the mixed layer, and shallow energy spectrum near the surface is consistent with unforced SQG dynamics, but not with QG. And in fact, what we've seen is that QG makes an appearance briefly in that little excursion to a minus 3.8 slope. And we also see something similar to our 1 and 2 layer barotropic results at mid depths. Okay, well, thank you very much, and I'm done.
Thank you. We have time for questions. Okay. That's fine. You can go first. Yeah. You're allowed to come first.
I was kind of trying to understand why the mixed layer wasn't all behaving the same, because it should be well mixed. But you did say something about resetting it all the time. Could you kind of go through that and explain it a bit better?
So basically, it's when I say mixed layer, so what it is initialized, the initial condition is constant buoyancy, okay? But then I let it go. So then it just evolves under its own dynamics, which is wind stress forcing, rotation, turbulence, vertical diffusion, but it slowly relaxes, I think, on a 30-day scale to a constant buoyancy profile. And so the buoyancy actually doesn't change that much. I plotted it instantaneously. There's small deviations, but the turbulent dynamics does change. The buoyancy maybe isn't the key point. It's that you've got wind stressing. The wind stress is dumped into that top very thin layer. So in the 60-layer case, it's a few meters deep, and then it has to get diffused down. And so it's this transfer of energy vertically through diffusion that I think is driving the difference, right? So you have to think, what's the key dynamical thing? But good question. That's a nice question.
So my question is, what do you think would happen if you put some nice big topography in the bottom?
Okay, that's a really interesting question. So I have another paper on not using wave-trisk on the Gulf Stream, and what we were trying to do there was precisely investigate. That was with Laurent Debrun and Patrick Marchesiello, Grenoble and Toulouse, and we were looking at the effect of topography. What was more important? Was it high resolution or accurate representation of topography and getting the Gulf Stream right? And it turned out we had a special way of getting the topography even at lower resolutions. It turned out topography is essential. It directs the Gulf Stream. So I would say if we were interested in actually knowing where our jets are going, yes, bathymetry would change a lot. I'm not sure how much it would change the actual turbulence spectrum, though.
Yeah, I just asked it partially because the breakdown of barotropic and baroclinic into modes is only true over flat bottom. So as soon as you put significant topography in there, you start mixing modes.
Yeah, and we only did that decomposition in the previous work when we had 2 layers. And then this other, 60 layers, it just does whatever it wants. But that would be interesting too, because we could put some significant topography in a 2-layer simulation and see, well, wait a minute, does that change something? And I guess what we would like is somehow it amplifies the baroclinic mode, and then that maybe can dominate. Because we were kind of questioning, why is that baroclinic mode so weak? And we tried various things to try to strengthen it to get its strong turbulence to dominate. We never could. Thanks.
Thank you. Let's thank for our next talk, Enhancing the Realism of Ocean Tides in Global Ocean Models by Zhengju Xu. This means you've talked for 9 minutes and you have 3 minutes more to talk. And there's room for questions after.
Okay, thanks. So today I'm going to talk about a little bit about tides from the global perspective. So tides are high frequency narrowband processes that affect the sea surface height and the ocean currents. Among all the tidal constituents, the M2 tide is by far the largest, which accounts for about 70% of the total tidal energy input. In contrast, the largest diurnal component, the K1 tide, is only about 10%. In terms of the tidal energy dissipation, 70% is dissipating in the shallow waters, and the other 30% is in the deep ocean. So in numerical models, or at least on the global scale, the tidal energy was input into the model through the equilibrium tidal potential and the self-attraction and the loading. And then the energy is removed from the system due to the bottom friction, and that bottom friction is about 70%, and it occurs primarily in the shallow waters. The other 30% is converted to internal wave energy, primarily in the deep and open oceans due to internal wave generation. So for those of you who work on coastal models, I'm sure you're very familiar with the bottom friction, but today I'm going to focus on this barotropic to barokinetic energy conversion in the deep ocean. So, and the effect of this energy conversion on the barotropic tides is a linear drag. And what's special about it is that this drag is frequency dependent, which means that the strength and dissipation of the barotropic tidal energy are different at different frequency bands. So this is why in the equation, in the term that represents this frequency-dependent drag, the drag itself is not applied to the total velocity. Rather, it is applied to the tidal velocity, and the combined effect throughout the entire frequency spectrum is represented by the summation of the drag at different frequency bands. Now, this gives us some difficulty of modeling the wave drag because the tidal velocity is not easily to compute when the simulation is for simulations running in the time domain. And for example, if you're using traditional methods such as the harmonic analysis, it's very computationally expensive, and it's not really feasible when we want to know the tidal velocity at each time step. So what we do here, we developed a filtering method which can perform this bandpass filtering to determine the tidal velocity while the model is running. And this is, we are taking a completely different approach from harmonic analysis. What we do is that we are using this second order ODE as the filter equation, where this omega is the target frequency of the filter, which is the tidal frequency you want to have. And this alpha is the bandwidth of the filter. So what it does is that it takes the total velocity, which is broadband in the frequency spectrum, as its input, and then it will give you the tidal velocity as the output. So sounds very simple, but why it works? If you recognize this equation from your undergrad ODE course, it's essentially just the simple harmonic oscillator. And if you think of pendulum, it has its own resonant frequency. Regardless of which frequency you force it, it will always want to swing at its own frequency. So the same analog is here in the ocean, in the fluids, where you give it, you force it with an arbitrary or broadband frequency input, it will always want to oscillate at its own frequency. So what we do is that we just incorporate this filter equation into the governing equation of the model. So when the model is running, the filter equation is time step at the same time. It takes the total velocity from the model, and then it will feed the filtered tidal velocity into the model. And there we go. So next, I will just show some results of how it works. So we implemented it in global MOM6 model, 112-degree resolution. I have results from both barotropic and baroclinic models, but I don't have time. I will just talk about barotropic model in this talk. So in this model, we are forcing it by 4 of the largest tidal constituent. And we are using self-traction loading from TPXO data, and then we're using the Nykander scheme for the internal wave drag. I will present 2 sets of simulations. In the first set, the simulation is forced by only a single tidal constituent, one in each simulation. So in that case, I don't have to apply the filtering because the total velocity is approximately equal to the tidal velocity, at least in the deep ocean. And in the second set of simulation, I'll force the run by all 4 tidal constituents. And in this case, I will use filter to extract each of the tidal velocity at each of the frequency, and then use the frequency-dependent drag to approximate this barotropic to baroclinic energy conversion. So the model performance will be evaluated by the root mean square error between the model output and the TPXO results. So I have a table showing the global area average RMSE here. As you can see, so for both sets of simulations, except for the M2 tide, the results are very similar. And for the M2 tide, the simulation forced by all tidal constituents with the filtering being used is actually have a much better result than simulations were forced by a single tidal constituents. And this is what it looks like on the global domain. Here, this I'm plotting the RMSE of tidal elevation in these 2 plots. The red means larger error in the simulation. The top panel shows simulation forced by all tidal constituents, and the lower panel shows the simulation forced by only the M2 tide. So the difference in the M2 tide is, well, I mean, on the large scale, it looks very similar, but if you look into the details, they are quite different. And remember that when I'm using the filter, it's a purely mathematical tool. I'm not introducing any physical forcing or dissipation when filters are used. So this means that by adding the filter to the simulation, I'm not adding any additional artificial energy or removing energy. If that happens, it must be occurring due to the interaction between different tidal constituents. So this plot shows the difference between the 2 simulations that I just showed in the previous slides. And the blue here shows the improvement when I have all 4 tidal constituents in the simulations. So you can see that overall, the simulation forced by 4 tidal constituents are better in general, especially in the shallow water areas, such as in the North Atlantic, where tides are actually the area tend to be the largest in tide models. And what this shows us is that, and basically the improvement occurs simply by adding and correctly modeling additional tidal constituents in addition to the M2 tide. And what it means is that the interaction between these different tidal constituents are actually very important if we want to correct model the ocean tides. So the conclusion from this work is that we have so in global ocean models, in order to correctly represent the barotropic to barokinetic energy conversion, we need to consider the frequency dependence of the internal wave drag. And this can be done by using the streaming bandpass filter to determine the tidal velocity. By doing so, we can correctly represent tides in different frequency bands. And then this allows us to better represent their interaction. Eventually, it will improve the performance of the overall performance of all tidal constituents. Thank you very much.
Thank you. Do we have any questions? Yes, Paul.
I'm going to go to your very last point on your conclusions.
Yeah.
Further improvement of model performance. That can mean a lot of things. So if I'm thinking about a model where I'm running it with tidal constituents, you're showing you can improve the energy conversion, those aspects. But if I'm thinking of the large scale fields, where am I likely to see the biggest impact? Is it in terms of the mixing, and then for maybe impacts on the hydrography, structure, the currents? I'm just thinking, where am I likely to get where do I really want to focus on understanding if I'm getting the tides right, so I can get aspects of the large scale circulation and hydrography correct?
Okay, so I think I'll step back to talk a little bit about the motivation here, because the internal wave drag parameterization is needed when you cannot resolve internal waves in the ocean model, right? So if you have a high resolution regional model which can resolve or at least partially resolve the internal waves, then this might not be as important. So this is why our effort is on the global scale. But on the global scale, everything is connected. So for example, there are many studies showing that if you improve the tides in the Hudson Bay, Hudson Strait, and the Baffin Bay region, it will have a basin scale impact. It will improve the tides over the entire North Atlantic. So I guess, and in the literature, people were trying to tune in the tides to get this particular region right. But what I'm showing here is that maybe one of the missing piece in the tuning is the interaction of different tides. So I guess so the point of further improving the model performance, and what I mean by this point is that I'm actually it's not just improvement of the accuracy, it makes the tides more realistic in the model. I think this is the ultimate goal.
Thank you. Yes, we can clap again. We have time to clap again, unlike this morning where it was like that. No, one clap, let's go. Moving on to our next speaker. Our next speaker is Luis Henrique da Silva, who is going to talk about analyze, handling and visualizing NEMO-ANA outputs.
Is this the pointer?
Try not to use the pointer.
No, not a pointer. Just the control.
Flip the slides, no pointer.
Yeah, no pointer, no
I will
pointer.
give you that when you talk for 9 minutes, and you have 3 minutes more to talk.
Okay.
Then we'll still have time for questions.
Perfect. Thank you very much. I really appreciate the opportunity to be here today in person. Last year I was talking on CMOS, it was online. I was talking about fresh water on Baffin Bay, completely different talk about it. Today I'm going to talk about something that is pretty new for me. Like I never talked about this kind of work before, mostly about ocean. But today I'm going to talk about analyze. Okay, the title doesn't deliver much, but let's go into that. So analyze is a Python-based package that we aims to be a toolbox for people to easily and simply access ANA outputs from ANA configuration from NEMO model. It's really specific here. We're talking about one singular configuration. You saw today through this afternoon that we have several configurations, but this is a start. So the idea is to simplify how people can access, visualize, and work with outputs from ANA and NEMO. The story behind. So how does it start? Emilio Enriquez, one of the one that is collaborators in this project, basically the brain behind this. It was a postdoc at our Porter lab, working with us, and he was shifting from astrophysics to work with ocean. And he had a lot of questions about it. How do we do our job? How do we study the ocean? What do we do daily or trivially or routinely on our work? I'm here that we had several chats, coffee, beers through all those days. And here I'm summarizing the 4 main topics that actually motivated the development of this package. So first we're thinking about standardized process, how people work with the outputs when they get into the lab, when they are a new student. What do they do? Do they have to come up from the scratch with their codes and everything? Or can they use something that is standardized and allows reproducibility? We have several codes using on the lab. Do we have a version control of this? If I change something and this breaks, how do I know how to get back? The third point there, and something that, well, I'm pretty sure I'm not the only one, and not even Emilio is the only ones that have heard about that. Someone in the past has a code, you have to figure out how to use that, and we're lucky the new version of the software that you were using still accepted those. From that, the last point, what if we had a way to simplify the access to the outputs, even for those that are not modelers, people that actually doesn't use NEMO? Well, sounds interesting. Now you got my attention, Emilio. So the idea, we thought about a Python-based package that would be on a repository on GitHub that does allow version control. The idea was to have standardized process, simple process that we do when we have a new simulation, a new output. That would, as I mentioned again, allows reproducible work. That also having a repository focused on analyzing NEMO outputs could allow in improved collaborations, right? Everyone can work with something different. And then you can everyone try to come up with the same codes in the same place. That will be easier to work with. And again, for me, one of the strongest points is to simplify the SS for people that doesn't use NEMO outputs. New students, summer students that are just undergrad that never touched on programming and anything, they're just like figuring out what they like to do. So how was it done? It's, again, Python. Why Python? It's a free software. And the Pythonian way to do things foster a collaborative and open perspective. The core of the package is a class and a dataset class, which is a wrapper of X-array. If you're familiar with Python, you know that X-array is the state-of-the-art of package to use to access netCDFs. So we are not trying to reinvent anything. We are trying to use what is the best right now and apply to our needs. While I'm talking here, you're going to see an example of how it works in that video, how fast you can plot less simple figure. So what it does, so basically reads and retrieve metadata in data, right? It immediately applies mask on the fly. So if you have a particular mask for a particular region, you just insert that in the code and that's gonna apply the mask and you're gonna slice down your regions. Oh, 3 lines of code, a figure, great. You can slice the area using light longs. You can see that everything is a little bit basal. It's very similar to what X-array does, but we have to start somewhere. You can write the netCDFs. Oh, you can change projections as well. And for me, the most important, right, the simplified plots that you can see. And behind the curtains, we are using Cartopy, GIS, VEST. We are using CMOS that also is CMOS that is using an idea of standardized process as well. Like they use the same colors for particular properties of the ocean. What a kind of application we have with the idea of allowing more people to access the outputs and to visualize that. The one step on this is using the analyze on the CanWin data hub. CanWin, Canadian Watershed Information Network, is a data hub from the CMOS at the University of Manitoba. There you can find a lot of observations from Hudson Bay, Lake Winnipeg. And the idea is to apply behind, we also have outputs from Juliana's, Marson's previous studies, but you cannot visualize anything. You have to download it and do your code and see what is inside of those outputs. So the idea of this first application for the package is to have a dashboard on the website, and anyone can access the website and couple clicks visualize the outputs. An example is Nick. Nick works in Hudson Bay, right? Anna, the Anna configuration covers Hudson Bay. Nick works with observation, but he's interested to see how is the overall area of Hudson Bay represented in the model on that particular day that they had a cruise and got some data. That, from my point of view, is the strongest part of this idea, right? I'm not trying to sell anything here. I'm just sharing an idea that we have, and from my perspective, a bit of work that we have been doing so far. Analyze is going to be constantly under development. So for now, we already have inside this 4 topics here. First one is an interactive mask creator. So if you are a new student working in a new region, you can, with a couple clicks, draw a polygon on a mask and have your own mask for your own region. Those 3, analyze temps, sol, and val, are what we are calling now as scientific classes. So the idea is to have a specific class to execute specific process and tasks for those 3 variables. For now, of course, we have a lot to cover. A little bit more in the future, those that from the previous slides are read already, like they just need to get some refinements to get online. Now, at this right moment, the version 0.5.0 only covers one single file, so you can access one single file. Again, we have to start somewhere. But we are working on it to use like multi-files that would allow us to do temporal analysis, create time series, everything standardized, reproducible, and easier for people that are not used to it. I know that Anna, from the name, is a specific configuration, but it would be interesting in some way, either within Analyze or a branch of the Analyze to also tackle other configurations. And another really important is availability on pip. If you are used it with Python, you know that you can install a package by running a simple line of code. This is not yet the case. For Analyze, you need to go to GitHub, clone it, and then install it by yourself. And where is the code? GitHub. So if you are interested, you can read like scan and that's gonna take you there. This QR code. And there we have all the codes that we have wrote so far. We have the README that's gonna walk you through the installation and process, and also a tutorial that's gonna show you the basal uses of Analyze. To wrap it up everything, Analyze is a toolbox to improve students and research workflow that aims to allow non-modelers to quickly visualize outputs. This kind of approach standardize the code, allowing version control and reproducibility, and also gives rooms for enhancement, constant enhancement, and new implementations, new methodologies that someone can come up with, can be applied on it, and use it for different groups all over Canada and the world. So thank you very much for your attention, and I'm open here for suggestions, questions, comments, and anything. A little bit different from the day, but thank you.
Are there any questions? Yes, Kyoto. Can you come all the way up here? It's okay, we've got time. No audio visual problems yet?
Hi, I was wondering if this was, maybe you mentioned it in the beginning, but I was wondering if this was something you worked on the side, like on the evenings and weekends, or if you maybe like received funding from somewhere to focus on this for a while?
No, I didn't focus. This is a side project. Okay. I work with Baffin Bay Freshwater. This is something like I have to write codes, and I see students coming and going, like, and having to rewrite their codes again and doing analysis that are maybe not the same pathway that they have when developing their own codes. That with this, we can we aim to at least give those persons like a standardized way, and we can like compare different results with from different people, because they're gonna work in the same way. So it's just a side project.
Yeah, I was curious because I think many people might have ideas to do something like this, but I think there is often pressure to not spend.
Well, Graham helped a lot, not working properly recently. I definitely we want to even have more time to working on it. This is, in my point of view, is just the beginning for this idea. Of course, I understand that a lot of people might have that idea, and like if there's someone that at some point started but it didn't continue it, we can try to join forces and like work together. Thank you very much. Thank you very much for your question.
So we have a series of tutorials or websites to show how to use our materials, but they were done many years ago and hasn't moved on from there, and certainly never became a package or an extra on top of X-ray. But we do have that. But yeah, this is really interesting to hear. Are there any other questions? Yes, Natasha.
I guess it's more of a comment. So we have something similar at CCCMA. Right now, it only works for the global model, but I think this is something that we could talk more about. It's not my section, but there are people. But then we can also maybe bring this up tomorrow at the NEMO workshop as well to kind of join forces and all that. So
Yeah,
it's a really awesome idea.
I never thought that I would be like the brilliant mind that came up with the super package. Of course, so many people working on it. Thank you. Thank you again.
Thank you very much.
Thank
and
you.
thank you for saying version control. Our next speaker is David Greenberg, who is going to give us an examination of daily averaged output from all ocean models. I put the all in.
Thank you.
This means you have
Yep.
talked for 9 minutes. You have 3 minutes more to talk.
Yeah.
Okay?
Yep.
Yeah.
Okay. So thank you. The inspiration for this comes from looking at model outputs. When you've got a high resolution, large domain model going for long times, you have a lot of output. As an example, the 3 ocean model running for a few decades outputs between 20 and 30 terabytes of data for a single run for those decades. And that is only averaged data, data averaged every 24 hours. 24-hour averaging can become problematic, and I will try to show that. Now, there is a right way to handle this problem. I'm not going to use the right way. Here's the right way, Walters and people. And we've been ignoring that for years. So I'm going to try to scare the life out of you with some pretty pictures, then come charging in on a white stallion to save the day. And then I'm going to fall off the horse. So, the problem. Take a look at the blue line. This is St. John. Now, this is going to show you the worst possible thing. Take a look at the blue line and take a look at the black line. The output from your model is the blue line. You're ignoring everything in the black. And that blue line is not a good blue line. So that's what I'm going to try to show to begin with. Here we have, I can almost read that. What you're really looking at, and you take a look at the blue line and the red line, and there's a blow up on the lower right there. If you were to take that 12-hour average and make it a running average, 24-hour average and make it a running average, you can see that there's an oscillation in there. The oscillation is because the tides aren't matched with 24 hours. They're something like 25 hours, and you're getting that spillover, and you're just subsampling that and producing frequencies that just aren't there. That red line on the right, you can see how bad that's happening. And then you're subsampling that and producing some fictitious sort of picture that is not really a nice thing to look at. Look at it a little bit more. Why am I looking at this? Oh, can I see it here? So let's take a look at at the reduced signal. Let's take the tide out. This is really what you want to get, just a tide filter. So we've done a tidal analysis and reduce it. You're never going to do that in a model. You can't do that. You don't have the time. You don't have the memory. But we can do it here. This is all data I'm looking at for everything to do with elevation. And you can see that we're all over the place. We're not really getting it. Now, if you do a 24-hour average of the tide removed, you can see that smooth line, which is really what probably what you're trying to get at eventually. So oh heavens. Again, we take a look at the 24-hour averages and that compared to the subsample that you're taking, and on the upper left, and again, we're not doing a good job in seeing what should be there and what should be our target. And if you subsample the real series, you're seeing quite a different thing from the blue line, what you're doing with a 24-hour average. Let's introduce a 25-hour average, which does cover it. And suddenly we can see, oh, no, not that. We can see the green line, which is our target, is now almost approximated by a 25-hour average. We've reduced that problem by a whole lot, and subsampling that will get us a whole lot better picture. And now, if we do the 25-hour average or the 24-hour average of the residual picture, we're getting the same sort of thing. So that is a good thing to have. So we think the 25-hour average is a great thing. Well, let's take a look at Yarmouth. Yeah, the blue line looks pretty bad, not as bad as it did in the in St. John. When we start looking at the different signals that you're getting, what it looks like with 25-hour, 24-hour, and compare that to the analyzed, the reduced signal, we're doing a much better job again with the 25-hour, but not as good with the 24. When we get to BIO, the Halifax tide gauge, the total signal compared to the residual signal, the average signal is not so big, and we're getting almost the same answer. So I've fallen off the horse. The 25-hour average is not going to be the answer for everything, but we'll try to take a look and see how these things work all over at other stations. And we're going to do some analysis of what's going on. And we're going to use the gamma squared, Keith Thompson's gamma squared method, which says just compares how well things work. If they reduce the variance of the difference or the variance of the signal, if they reduce one is better than the lower than the other, then it's clearly better. We also look at the root mean square error. And in both cases, in almost all cases, they're better. There are two cases where it's not, and they're on the West Coast where K1 tides are dominant, and we see that we haven't done as well in elevations there in Victoria and Campbell River. So the 25-hour average isn't doing you any harm in every cases, and in many cases it is at least a slight improvement. And a big improvement where the M2 tide is strong. Now, let's think of currents for a second. And when I start looking at currents, I'm looking just at currents coming out of a 2D barotropic model. And just so that you compare the currents that you see above with the tides below, from continuity, you think, oh, yeah, okay, if you know the tides, the elevation tide by continuity, the currents are going to be just the same. It's just gradients, but that's the transport is going to be compared to that. By the time you throw in bathymetry and other things, it's not the same. So we have an amphidrome in the middle of the Gulf of St. Lawrence, right by the Magdalen Islands, and that's a critical point that we look at. And there's the K1 amphidrome off to the right on the continental shelf, and we see that currents are very different. Some of them line up with what you see. Yes, there's low currents by the Magdalen Islands, but not so much around the K1 amphidrome on the continental shelf. So yeah, just looking at the currents that what you see in the elevation isn't going to help you a whole lot. here's what we get for depth average currents on the Atlantic coast and the different error measurements. And yes, well, certainly in the Bay of Fundy, boy, you're really winning when you're looking at gamma squared or the RMS squared. You're getting a much better answer towards your residual at the different places. And the other places, in this case, in just about every case, you're doing at least a little bit better, and in no case are you doing any worse by trying the 25-hour average. Now, just to remind you that your look in place like Cap Mul, which is the Magdalen Island, the signal that you're seeing there is almost the residual signal is almost the same as the tide. The tides are very, very low there. So when you take a look at what you're getting for your analysis, when you've got a 24-hour or a 25-hour average, you see how I guess on the lower right, you see how your 24-hour average is not doing a good job of even subsampling the continuous signal. And just to keep in mind that you are missing a very big piece of the signal when you are just looking at 24 hours, and somewhere, if you're trying to think about where things are going, think about if you're sitting in front of a bay at high water and trying to track something, and therefore the water is coming out of the bay, a particle at the mouth you'll probably never see again. If you're looking at it at low water and the tide is going to start on its way in, you could be trapped forever. And we'll skip that and go right to the conclusions. So 24-hour time averaging can introduce spurious results due to the presence of strong tides with periods 24 hours, greater than 24 hours, M2 and N2. 25-hour time averaging is less problematic, but not perfect. And what is being averaged away should be justified in the context of the process you're studying. And it's probably a good idea to at least check a few short time series of full-time resolution without averaging to look for anomalies that would otherwise not be seen. Thank you.
Thank you, Dave. Are there any questions? Sure, go ahead.
So obviously, if you're looking at the tides and that you're interested in that higher frequency, but say you're interested more in the larger scale, seasonal to annual turnaround variability, and you clearly showed that 24 hours is leading to some phase issues with the tides and that. Would it be then better if you're not interested in the real high frequency with models to look at snapshots with outputs rather than averaging? Like, I guess it depends obviously on the scientific question, but this is maybe suggesting that the traditional, you might want to look at, just what is at given times rather than averaging over those periods.
Yes, I think so. I think that certainly has a big part. A lot of verification of models based on the average surface salinity of a basin. And what? that isn't a verified model. Yes, it's nice. That's something that you want to make sure you've got. But yes, taking a look at the spatial picture and a snapshot, it is going to tell you something. At least you start getting into biology and the rest of it. What is going to be exposed at what time, and you take a look at it in the average. You might never see that part of a bay is exposed to a high salinity, low temperature, or whatever. In that case.
Yes, come on up. Hey, David, this is a question.
You're not getting away that easy.
Sorry.
You're smart. I didn't say that. I'm watching what you're doing, and we were taught never to alias. Remember?
Yeah.
But you can alias.
Well, you sure can.
It it's a way of getting rid of frequencies if you're judicious. We actually do this because it's really expensive to sample. Like I'm working with hundreds of kilohertz data, acoustic data.
Yeah.
But my bandwidth is not that big. It's like, so you could do something like what Paul is suggesting.
Yeah.
Just slice every fourth sample, and you might be able to resolve this problem very cleanly.
Yeah, if the frequencies that you're looking at are not 2 samples wide.
Well, yes, but you're not interested in the tides, you're telling me.
Yeah.
So they'll just kind of wash away.
Sort of, except the way that you're slicing may introduce something that isn't there.
No, but you'd be demodulating the tide. It's just a thought.
Okay, so I'm going to try and figure out how I can do 25-hour averages. So now I would like to move to the next speaker, please. Our next speaker is Kyoko Oyashi, who's going to talk about a nested grid modeling system for simulating circulation and sea ice over the Northwest Atlantic Ocean.
Thank you, Susan, for the.
This means you've talked for 9 minutes.
Okay.
You'll have 3 minutes to talk and
Yes.
3 minutes for questions.
Great, thank you. Thank you, Susan, for the introduction. Hi, my name is Kyoko. I am currently at DFO, but until March, I was at the Oceanography Department at Dalhousie, working for Youyu Lu, who has asked me to present this talk on his behalf because of his travel schedule. This is a brief overview of the work that our group has been doing the past few years. So it will include work by several students and postdocs, and it will also, of course, incorporate help from several people from outside of our group. So I will start by briefly describing the motivation of our work, then describe our model, some validation work, then move on to 2 examples of applications, both in Nova Scotia, and conclude by talking a little bit about our ongoing and future work. So the main area of interest for our lab group has always been the Northwest Atlantic, which of course is interesting because of the many interacting processes such as the subpolar gyre and the subtropical gyre meeting near the Grand Banks of Newfoundland. There's also the outflow from the St. Lawrence River, strong tidal mixing in many locations, but also what happens in this region has global implications because in the Labrador Sea, there is deep convection, which combined with the high biological productivity of this area means that this area can be seen as a biological carbon pump in the global climate system. And a key factor in the physical environment of this area is sea ice, which affects things like the surface stress, surface heat flux. It can increase or decrease the salinity depending on the season. So if we want to simulate the physical oceanography of this region or the oceanography of this region, then we have to couple the model to a sea ice model. And the way we do that is to use ROMs for the circulation and sites for the sea ice model. We also have several configurations of nested grids because that way we can include as much as possible of the larger scale influences while also having a relatively finer grid resolution in our main area of interest. So this was one of our original configurations where the outermost model, which we call L1, goes from Cape Hatteras to southern Labrador. And then the innermost model, which we call level 3, focused on the southwest Scotian shelf. So in the next few slides, I will show results from this configuration, but we also have another outermost model, which I will talk later, and that one goes all the way up to the middle of Baffin Bay. So in this slide, on the left-hand side, I am showing the surface salinity and currents from level 1, the outermost model, but within the black outline, we are showing the output of the level 2 model, which is nested within the level 1 model. So if you look within the black outline, you will see more details in the simulated fields. And then the right-hand panel is the same thing, but with the level 2 and level 3 models. So moving on to validation, this is work by Albert Pei, who is a student in our group. One of the things he looked at is the tides. So we're showing the simulated tides from our model on the left, the results of a data assimilative tidal model on the right, N2 on the top row, and K1 on the bottom row. So our model is performing fairly well. It gets the amphidromic points and also the large tides, the large N2 tides in the Bay of Fundy and Gulf of Maine. And then another thing he looked at is the sea surface temperature. So here Albert averaged the simulated SST over the Southwest Scotian Shelf in the top row, the Gulf of Maine in the bottom row, and he did the same thing with satellite observed temperature. The red line is the observation, the blue line is the simulation. So the model is doing quite well. And the next slide shows the same thing, but for the whole domain. And he's showing the results for spring in the top row, fall in the bottom row, simulated results on the left, and satellite observations on the right. So I think we can say that this model is performing reasonably well. So moving on to applications. The first example is Halifax Harbor. So in this example, we are using a 4-level nested grid system with Halifax Harbor included in the northwest corner of our innermost domain, which is shown in the bottom left panel. So Halifax Harbor is a big estuary with the Sackville River at its landmost, at its landward end being the main source of fresh water. So as shown in the bottom right panel, the temporal mean simulation has the classic estuarine pattern with seaward flow near the surface and landward flow near in the subsurface. But once in a while, there is intrusion of saltier water from the offshore into the harbor. And one reason this is interesting is that at the, well, I'll go back for a moment. So at the landward end of the harbor, the northwestern end of the harbor, there is an area called Bedford Basin, which is a somewhat isolated basin with a depth of about 70 meters. So it is hypoxic in the deep waters. It is isolated from the rest of the harbor by a narrow sill called the Narrows. So some people call it a living harbor. And because of its proximity to the Dow campus in BIO, it's been monitored weekly for the past few decades. And so the occasional intrusion of deep water into the harbor means that if the intrusion goes far enough, then the Bedford Basin is ventilated. And unfortunately, we don't have an example of a full ventilation of Bedford Basin, but in this example, we can, this is modeled salinity, and the landward end of the harbor is on the left, the open ocean will be on the right-hand side, and if you can, and this covers a few days in the summer, and if you look at the 31.5 salinity, the isohaline, then we can see that it does make it all the way to the end, to the seaward end of Bedford Basin. And we can see that the 31.5 isohaline goes all the way from the surface to the bottom of the Narrows. So this was one example of the application of our model. And the other example is Brador Lakes, which is in Cape Breton Island, Nova Scotia. So this is the configuration we're using for the Brador Lakes. This is work by Shenmu Yang, who was a former postdoc in our group. So the Brador Lakes is an inland lake system with a connection to Cabot Strait at its northeastern end. And so Shenmu set up the model and did some validation work. Here he's comparing the simulated SST to in situ measurements at 3 locations in the lakes. And as you can see in the right-hand panel, the lake system consists of several basins, many of which are quite isolated from each other. Thank you. So that means that there is a large spatial variability in the temperature and salinity of the region of the lakes. So that in and of itself is quite interesting. But another reason we want to look at this, at the lakes, is that last time we checked, there were about 30 provincial licenses that had been issued, approved for aquaculture in the lakes. So we wanted to apply particle tracking to estimate residence times in the different basins of the lakes. So here, the particles were released from different basins of the lakes. The particles are color-coded by the depth at the time, and because they were released near the surface, they start out being a dark blue color, and then the warmer colors that the particles show at the end means that and these are passive particles, so with time they are moved around vertically as well as horizontally, and we can see that some of them move out into the open ocean through into Cabot Strait, but many of the particles are still trapped in the lakes after 90 days. So the resonance times that we estimated from these results from the resonance times range from just a few days to basically undefined. This is partly due to the fact that our model grid size is too coarse, and if we had finer resolution, maybe we might get better results or more particles exiting the basins in the particle tracking experiments. So to conclude, so this is ongoing work, and we only talked about we only work on the physical aspect, but there is a biogeochemical component to ROMs. So Professor Cajafeno at Dalhousie is working on that part, and our group, the next step is to couple a wave model to the existing system, and our group will be part of the Transforming Climate Action program that is sponsored by the Ocean Frontier Institute. This is a new multi-year, multi-institution program, so we hope that we can contribute to observations and modeling work complementing each other. So thank you.
Do we have any questions? Okay, so I get to ask the first question. So in your particle tracking, did you add a random walk component to represent the turbulence in the system?
We did. I don't think we added a vertical component. I think it was just a small horizontal component.
Okay,
Yes.
Interesting choice. And what was your grid spacing in the Brador Lake? In the horizontal?
I have to go back because I don't remember.
Sorry.
Oh, there 700 meters.
700 meters.
Yes.
Okay. Thank you very much. Sorry. I am looking at it kind of sideways. That's my excuse. Any questions? More questions? Do we have any questions online? No. Okay. Thank you very much.
Thank you.
Back up to the first slide. You're going to see the talk backwards. And fast.
Okay. I think we're just going to go ahead and start a couple of minutes early. And so the next talk is given by Paul Myers, and he's going to talk about modeling the Arctic Ocean and the Labrador Sea at 1/60th of a degree.
So yeah, I'm going to talk about development of very high-res models and what they may be able to bring us, as well as some of their limitations in that. And despite saying I'm giving the talk, this work from large numbers of people have contributed to the modeling system over the years as we've continued to develop them. So as a bit of outline, I'll give a bit of background. Arctic and Atlantic circulation, important of exchanges between these basins, even though previous speakers have talked about that. Motivate things, discuss the models and configuration we're using, show some preliminary results in the Arctic Ocean, Baffin Bay, potentially the Labrador Sea if I've got time, and then lead to discussion and thoughts on ongoing work. So people have seen slides like this, high latitude circulation, they're linked. The Arctic has flow in through from the Pacific to the Arctic. There's the Beaufort Gyre. Atlantic water comes in underneath that brings out heat that could potentially affect from the tidewater glaciers to the sea ice in the Arctic. The previous speakers have talked about. Subpolar gyre is cyclonic, boundary currents around the edge of the basin, convection in the interior of the basin, especially the Labrador Sea, all of which are important for regional ocean features as well as climate, as well as ecosystems and everything else. We also have previously were told that Beaufort Gyre is getting fresher in the Arctic, changes in time, links to many processes, and all of these are things we want to understand. What are the underlying physics, what drives it, and then how might that change going forward as we continue to look at a warming climate. We also know Arctic and Atlantic links are important. Fresh water affects the Arctic, storing all that fresh water, affects salinity, affects density, which can affect convection, deep water formation, ventilation, gas sequestration, potentially the AMOC, many questions. So there's a lot of reasons to want to study the high latitude system. We also have a lot of reasons why we want to look at for high resolution. These are older studies, but for example, if one looks at, oops, I should be using the pointer after I've told people not to, but if one looks at the black dot in the buoyancy plot, the maximum buoyancy loss in the Labrador Sea from the air sea flux is in the northern Labrador Sea, but the bottom right plot, which shows the depth of convection from observations, has the depth of convection farther south. So region where there's strong buoyancy loss in winter that can drive that deep mixing, but not where there's the most. Why is that? That's because of exchange of buoyancy laterally in the Labrador Sea. Eddies, especially shown in that plot on the left, Erminger rings, processes bring water that stratifies the northern Labrador Sea, then vertical eddy fluxes mix that upwards, so that you've got the buoyancy loss from the air sea being balanced by the lateral exchanges, so you don't get deep convection, unlike in this place where the eddies don't reach, and then that deep convection can just, that strong buoyancy loss can just erode the stratification, lead to deep convection. So, and eddies are driven by small-scale processes, baroclinic and barotropic instabilities that need, especially at the high latitude, as the Rossby radius gets small, you need very high resolution to be able to resolve and represent these processes. So we've been modeling for many years this ANA configuration, 1/4, 1/12 degree, looking at many questions in this region, trying to answer these questions, but always having limitations that this resolution is nowhere enough to really resolve eddies. It's eddy permitting, but not eddy resolving. And this is an example in the Arctic. Tahya showed this earlier today. This is from simulations, global and regional simulations, looking at the freshwater content in the Beaufort Gyre compared to the observations. The black line is the Proshchenutski's observations, and all the lines below, falling below, all the different colors, are from our regional simulations. They don't do a good job of representing the freshwater there. The global simulations do. However, if you look at the inflow of the transports at Bering Strait, where those global simulations do allow feedbacks, they're getting the right answer for the wrong reason. Their salinities are off, the transports are off, and there's compensation of errors. So that suggests, again, there's more dynamics we need to look at if we want to be able to model this properly. And this is a good slide from a number of years ago from a paper of Bob Hallberg that showed sort of the needed resolution if you want to start resolving the Rossby radius. Even this the first baroclinic Rossby radius. It's small in the ocean. Tropical regions are fairly easy to resolve, but especially when you get weak stratification in the Arctic shelves, you're seeing that you need resolutions up to 1/50th or even more if you want to even resolve that first Rossby radius. There's going to be questions about how do coarser resolution models represent those important small-scale features. So previously we've done work, and I've talked about CMOS before, where we went to a 1/60th degree in the Labrador Sea using a triple AGRIF or a double AGRIF nest. So resolution's down to 1 kilometer, as shown in that bottom left plot. And the motivation is that can resolve the eddies. I'm just going to play those two for now. Bottom, the left figure is the vorticity. The right one is the convective resistance. This is, unfortunately, I've got to mislabel my slide. Is convective resistance, looking at, again, how resistant that upper level is to buoyancy loss, mixing the stratification. And you can see it's very high up where you've got all those eddies. Those eddies are fluxing up, very buoyant water, increasing the stratification, opposed to the convection. While farther south, where the eddies don't reach, that is where the stratification is weaker. That's where we get convection, again, suggesting the importance of eddies. And so high convective resistance values, strongly stratified water column. So, and again, the role of resolution, we've got our 1/4, 1/12, and then the 1/6 degree simulations. The 1/4 and 1/12, you really would see with a very low convection here. The whole laboratory turns over. It's not that the models are getting deep convection compared to, say, the article flows. It's that they get occurring over a much too broad area, which leads to much too strong overturning and effects on the overturn, the AMOC, etc. Versus this much more stratification, much more limited areas of weak stratification in 1/60th, which suggests again, the importance of eddies, the importance of resolving things at these level layers. I'm just going to actually skip ahead for time. So, given that 1/60th is really good for the laboratory, we decided to bite the bullets and run the entire Arctic and subpolar gyres at 1/60th. Previous speaker talked about the amount of output coming from, for example, the CANTOD system. We get 7 terabyte in here. So there's all sorts of technical issues, but we really want to run the whole Arctic Ocean. You can see this rate, and especially, I would have liked the southern boundary farther south, but I don't know if you do cost issues, but I want to allow exchanges around southern Greenland. There's tides in here, river runoff, see all the sort of typical features there. I can talk about them. And the bottom plot shows, except on some of the Siberian shelves, we're at least resolving with at least 2 grid cells at first rod radius. We're going to likely get a reasonable representation of the eddy processes. And as an example of that, I've got 2 movies. One on the left is the entire Arctic Ocean, and the one on the right is a blow up of just the Beaufort Gyre region. And what I'm showing is the average speed over the top 200 meters. You can really start to see eddies forming, currents, how variable the flow is. Not that it's just a mean average flow. Note that I only have about 6 years of output. We've only been able to run this. We started this in 1993 with the Area 5 forcing. We've got 8 years of output so far, which we're extremely excited. We've got still a long way to go before we get the next 20 years doing a 30-year integration. And of course, that's the limitation of high resolution model. You don't get an ensemble. You get 1 member. If we're lucky, we'll eventually do 2. And I might get the second before I retire. But again, there's so much structure, so much details, things we want to explore and look at. But anyway, so yeah, look at so on the top left is again the convective resistance to the top 100 meters. So again, showing where the stratification. You can really see the flow coming up the Siberian rivers. When the movie gets to summer, you can see plume of eddies coming from Mackenzie and going into the Beaufort. You can see the transport drift and again the role of all those small scale features. The one on the right is the convective resistance for the whole Arctic, again, shown more. The one on the bottom left is the freshwater content. So again, you can see where that freshwater is coming into these regions. Role of the small scale. The one on the bottom right is not playing. We're supposed to be getting kinetic energy. It's a snapshot, lots of eddies, because I wanted to compare with some of the mooring data, which is what we're on the trying to do. But again, lots of structure, a lot of details. Beaufort Gyre freshwater, as I said before, not doing a good job of course resolution. 1/60th. We're not as far along as the observations, so I don't have the observations yet, but it looks like it's going the better way. Those small scale features are really helping the features. Baffin Bay. This is seasonal circulation, and as the season on, you're suddenly going to see high frequency currents and lots of eddies forming around the coast near Greenland. Likely related to the melt from Greenland, fresh water, setting gradients driving those flows, and suggesting there's a lot more exchange between the fjords, the interior, the currents, than is suggested from previous course resolution models or even a little bit of observation. So additional features we want to explore given the high resolution model, and we're also interested in For example, where the fresh water gets offshore, how the water coming from Baffin Bay gets into Hudson Strait, how does it go south, where does it get into the Labrador Sea, mist exchange, how does it get taken up in the subpolar. These are again just pretty movies. The detailed science is still ongoing, and that's again one of the problems. There's so much data, it takes so long to process it. We keep running out of memory and everything else on our servers and our systems. Never mind all the issues on the Digital Resource Alliance system. Canada has got all the supercomputers down right now. So in summary, we've developed a 160-degree panoramic Nemo configuration. Everything from tidal forcing, icebergs, all sorts of bells and whistles in there. We've got 6-7 years where we're getting into 2000. Significant increase in the eddy activity in the Arctic and the subpolars. A lot better eddy generation, a lot of barotropic directly instabilities occurring. Comparison with observations to actually evaluate, and that's going to be a challenge given the scales are ongoing. There's definitely improvements. I didn't have it here, but for example, for comparison, I sent some of the model fields in Baffin Bay to Bob Picard to compare it to with detailed observations from cruises, and it suggests the 160 actually compares well, much better compared to the coarser resolution. I didn't have sea ice here, but the sea ice linear kinetic features starting to show up at this resolution. Seasonal circulation eddies, lots of things ongoing, lots of things that we need to look at and improve. And the other thing I'm going to add, there's so much output, we can only look at so much. This is something that's trying to be shared, because if other people can look at the model and find more of our problems, we can try to fix them, that would be great. But this is where we're going. I really like looking at the high resolution, what's going on, so we can then try to improve the coarser resolution to say we just get from climate downscaling studies to climate models, and I'll stop. I actually finished on time for once.
I think you need to thank Kyoto for giving you an extra 2 minutes. Does anybody have questions before I go? Yes, David.
With such a large model and so much output, I can't imagine you can do too many sensitivity studies. But okay, one thing that I worry about a little bit is Hudson Bay being cut out completely, and where.
It's not. That was just the move. Oh, sorry. No, we include Hudson Bay. It's fully included. What the issue is with the movies, we can only put a certain part of the data on the disk. So
Okay.
That's the cutout that Clark, who worked for me, has been playing, moving in and out. Oh,
Okay.
we want to look at the subpolar gyre this month.
Yeah.
Put on
Okay.
that,
Yeah,
put
okay.
on whatever.
Good enough. Thank you.
So, but yeah, that is a good point. But I guess the other thing I didn't say, I will say, the other big concern, which actually maybe relates to Nicholas's talk at the start, as you improve horizontal resolution, how should we be improving the vertical resolution? Because I don't think we've done that well enough, but that's another whole topic.
Okay, so my question is, have you considered serving this data on an ERDAP, these results on an ERDAP server, because you could keep 7 teams busy with this output?
I would love to do so and explore getting it done properly, yes.
Good, good.
I haven't done it, it hasn't been done yet, but it would be fantastic.
Do you have it on local disk?
I have it on both local disk as well as track systems, yeah.
Okay, so it should be possible.
Or it will be on local disk as of the next week or so, since we just got our new 200 terabyte disk in place.
Given that it's local disk and given that you're a university, it can probably be done.
Sure.
But you can reach out to our group if you want for some suggestions. Because I really, it's been wonderful actually to see the many different people who use the Sailor CCast output, because I put it up online. And I think, you know, with these enormous simulations, which are super exciting, plus some tools for people to look at it. But you're going to have to think about how your tools can use stuff from ERDAP, right? From serving it on something like an ERDAP server, but that's really good.
Yeah, no, we've already shared with a lot of people.
I know you share it with lots of people. I'm not complaining.
But yeah, there's some manual steps, and I agree, improving that would be very
It would be really super. Does anybody else have any questions? Okay, I'd like to thank all our speakers and all my co-conveners. We have a really long list of those. I think the plenary tomorrow morning looks really interesting and is from local Saskatchewan. After coffee tomorrow morning, we are meeting in Gallery D in particular to discuss the NEMO and what? At 10. Sorry, at 10 we're meeting. Yeah, come down and take your coffee there. And we're going to talk about more about models and particularly about NEMO. But non-NEMO modelers are welcome.
In fact, one of the questions would be, should we turn the community of practice to just general ocean model? So for those non-NEMO modelers, it's a topic.
It certainly used to be. It's gone back and forth. And so, yeah, and we can definitely learn from all models. Thank you all very much and hope to see you tonight at the banquet.
It's on the, it's just, finding time, getting it sorted out. Yes. Yeah. And ideally what I'd like to do is find some way, like way of our should be getting some money to really get someone